Sampling and Sampling Distributions, Chapter 8.1 through 8.4. We're going to start this chapter with a review of some terminology. The population is the entire collection of all individuals or objects of interest. So when we talk about a population, we could be talking about people, or we could be talking about things like products. The sample is the portion of the population that is selected for study. So from the entire population, we pull individual people or objects of interest, and our sample is a smaller subset of that population. The branch of statistics called inferential statistics is the process of using sample information to draw inferences or conclusions about a population. So here's our population, and imagine that we poll that population in some kind of random fashion, and we extract some elements from the population, some objects of interest from the population, and then those objects of interest or that random sampling becomes our sample, a smaller subset of the population. In inferential statistics, what we do is we look at our sample, we do statistical analysis on our sample, and based on the results of that statistical analysis, we then make conclusions or inferences about the population from which the sample came. Okay, we're going to start with an activity where this activity is slightly unrealistic, but its purpose is to simply help you understand the mathematics that goes into sampling. Let's consider a small population of 5 commuters who are all neighbors. So very rarely is a population going to have as little as 5 things in it. But for the purpose of this exercise, we're going to look at this simple exercise. So what is capital N? Well, let's remember that the definition for capital N is the size of the population. Therefore, capital N is 5, the size of the population. So let's suppose that each commuter was asked how many miles he or she commuted to work each day. Okay, and from the whole population, we have 5 miles commuted to work each day. So commuter 1, 50 miles, commuter 2, 84 miles, commuter 3 is 38 miles, commuter 4, 120 miles, commuter 5, 48 miles. So each member of the population has got a mile associated with them. Find the population mean of the set of data. So how would you go about finding the mean? Well, it's only 5 values, so it's easy enough to just add up those 5 values and divide by 5. So if you go to your calculator and just simply sum up 50 plus 84 plus 38 plus 120 plus 48, okay, get the sum of the 5 values, then divide by 5, you should get the population mean, and it should come out to be 68. Okay, and we symbolize that population mean with a mu, because that's the symbol for the population mean. So here mu equals 68. Find the population standard deviation. Okay, well, for this, we're going to have to do a little bit more work. And after we learned how to do this on the calculator, I had mentioned that the calculator should be the way in which you find the standard deviation. I mean, we learned how to do it by hand the very first time, but in the future, I said the calculator would be the best way to do it. So let's go to our calculator, and we're going to enter the 5 values into a list. Okay, so we're going to put in 50, 84, etc. Okay, I'm going to empty out list number 1, clear it out. Okay, so we'll enter in 50, then 84, 38, 120, and 48. Okay, once the data is in a list, to find the standard deviation, we press Stat over to Calc. 1var stats is our function for finding the standard deviation, so hit enter. The list we're going to use is my L1. Leave frequency list blank, calculate, hit enter. Okay. And there's the mean that we found earlier. It was 68. Now the calculator, we had learned this earlier when we discovered this feature on the calculator. The calculator doesn't distinguish between mu and x bar because the calculator doesn't know if the data you've entered represents a population or a sample. So it's up to you to put the proper notation on paper. The calculator is just using x bar regardless of whether it's a population or sample. The standard deviation, okay, we have Sx and we have sigma x. The one that we are going to use is the one that represents the population because we have our values representing a population of 5 commuters. So the population standard deviation is sigma x, which makes our population standard deviation 30.2787, and we're going to round to 4 places when we see the standard deviation. Okay, so 30.2787 is denoted by sigma for the population standard deviation. Okay, so now that we have those two values, let's assume that our population is of 5 commuters. It's too difficult to actually catch all 5 commuters at the same time to get the information needed for the study. So let's suppose instead of looking at all 5, we have to sample this group and use the sample information. So let's look at a sample of simply 2 commuters. So little n equals 2 in that case. And let's find the mean of the sample, which is represented by x bar. And we're going to use the mean of the sample as a way to estimate mu. Okay, we don't necessarily, let's suppose that we sample because we don't really know what the true population mean is. Well, when we find x bar, we're going to hope that our estimate comes close to what the real population mean is. So let's look at the first two, C1 and C2. So if we look at C1 and C2 and they become our small sample of 2 commuters, we can find the sample mean simply by adding the 2 and dividing by 2. So 50 plus 84 divided by 2. And if we find out what that sample mean is, we get 67. That's pretty close to what our population mean mu is. Okay, so we happen to pick 2 values from the population that created a sample mean that was pretty close to what the real population mean was. So if we list all the samples of size n equal 2, note that there will be 10 possible samples. Now this is a very important concept to understand. You're going to look at all 5 and you're going to create groups of 2. So if you look at all 5 commuters and you create all the possible groups of 2, you have C1, C2, then C1, C3, then C1, C4, then C1, C5, and then C2, C3, C2, C4, C2, C5, C3, C4, C3, C5, and C4, C5. These make up all the possible combinations for samples of size 2. Okay, there's no other sample of size 2 that you could come up with that's not in this list. Now, each of these represents a possible sample. So for C1, C2, the data values that make up that sample are 50 and 84. Now on the handout that you should be following along with, you'll see this chart, and in the third column I would like you to find the sample mean for all of the possible samples. So we already found out that the sample mean for the sample of C1 and C2 was simply 50 plus 84 divided by 2, which was 67. To find the sample mean for C1 and C3, we simply add 50 plus 38 and divide by 2. And you're going to put that answer in the third column. Okay, so take a minute, pause the video, find the sample mean for all the possible samples. You will have 10 values here. 10 different values for X bar that represent 10 different possible sample means. Okay, and these are the answers you should have gotten for the sample means. We did this one together. So if our sample was composed of C1 and C2, then the sample mean that came out was 67. If on the other hand our sample was C1 and C3, the sample mean comes out to be 44. If our sample mean happened to be C1 and C4, our sample mean comes out to be 85. Notice the range of numbers here. There's quite a range of numbers. Now, when we look at these possible sample means, some of them are pretty good estimates for the true population mean. Others are pretty far away. Okay. The data set of all the sample means in column 3 has a special name. It is called the sampling distribution of the means. Sampling distribution of the means. A distribution, let's remember, is a collection of numbers, collection of data values that we've seen in the past. We've seen them as data values. In this case, our distribution is not individual data values, but actually sample means. So it's a sampling distribution because the distribution is composed of individual sample means. Okay, it is a collection of all the possible sample means for samples of size 2. So the sampling distribution of the means is a collection of all the possible sample means for size 2.